met was last Thursday. We had a half a day, and as to be expected, we didn't quite get done with chapter 20. It is a long chapter, and as you know, I didn't do anything on conduction and convection and radiation, how the energy transfers. So that's what we're going to pick up with. Just to kind of review, and I guess I already started. You remember last Thursday, and these last 3 days, that Thursday, Friday, Saturday, have just been very busy days for me and Don. So we didn't have the MC on Friday, and I'm very glad that's all that stuff is behind us. And because of that, I said we're going to, get as far as we can, and would encouraging you to do as much as you can into chapter 20. But of course, didn't really expect you to be able to do all of it and go forward, so because we're not done. And so that's where we are. So even though the syllabus says we're starting chapter 21, and we may start chapter 21 today, if not today, definitely Thursday. But that's going to put us a little behind. But that's my goal, to finish talking about 20 and then do some examples from 20 and then get into 21 before the week is out. I thought there was something else on my mind here. It was the homework. So obviously a number of you are wrapping up chapter 19, and that's perfect. Just wanted to make it clear. I didn't really expect anybody to finish chapter 20, and some of you emailed me and were concerned about that, and no, that wasn't the plan. We're behind a little bit because of A, it was a long chapter, and B, it was all the stuff was going on last week. So I'm busily trying to catch up on everything, including some homework stuff to give back to you. So here's a big pack. If you want to dig through it now, great. If you don't, I'll put it out into the lab, into that little box there, and you will see that box accumulate just like you have in past semesters, as people will go there more towards the end of the semester and find their old homeworks. You still have the link I sent you right after the first test, or half test, that has your scores. So if you keep clicking on that, you'll see your homework get recorded slowly but surely. And then finally, let's go into this last chapter on the last part of the chapter, I guess I should say. And so here's what we've been doing. We've been taking things and saying, okay, this object is hot, and maybe I'll put it next to this object, and this object is cold. And we say, okay, the energy was transferred from one to another. We called that the heat. We labeled it Q. And we calculated some numbers, and maybe they'd come out like 100 joules or 200 joules or something to that effect. But the one thing we didn't really explain or talk about in this heat transfer is how quickly does it take place. I mean, it's one thing to talk about, hey, it's 100 joules, but it's a whole nother question to say, well, how long does it take for this 100 joules? And so the two questions to ask here are, number one, what's the rate at which that energy is transferred? And number two, just physically, how is the energy transferred? And we kind of touched on that, because the answer to that come in three parts. And the first one is called conduction. And this one is a molecular picture, and one that I kind of already explained back in chapter 29. As I said, your author kind of holds off until chapter 21 to really get into the microscopic picture. But I think it's useful to do it early, and this is a good example of that. Your author draws a little picture here, and he says, look, what if you were to take a metal pipe, or a metal, I shouldn't call it pipe because that makes it sound like it's hollow inside, but a solid metal rod, and on one end of it you make it hot, so we'll call this temperature T2, and the other end is, say, cold or cool or just room temperature, as I will demonstrate here in a second, but it's at a different temperature. What's going to happen is this. The rod, of course, is made out of some material. Could be copper, could be aluminum, could be brass, could be steel, and I have all of those up here. But all of those materials are made out of molecules. And what's going to happen is these molecules that are on this end of the rod near the hot object are going to start moving fast, because the reason we called it hot is that these molecules were moving fast. As they move fast, they hit these, which make them go fast, which then hit these, which then hit these, which then hit these, you know, and you get the idea. And eventually then this end of it gets the energy. And so there is a rate of flow. Q per time. Energy per second. At what rate does the energy move from one side to another? And that's what we're talking about. This question here. How does the energy move? Well, it's collision from one molecule to another, to another, to another. And that process is called conduction. I want to point out, notice in the process of conduction, how the heat moves. Did the molecules that are hot here go over to here? Did any molecules actually move from here to here? Yeah, they don't actually move. And I say that because that's the important difference between this and what we'll see in step 2, which is convection. So convection and conduction often get confused here. And so I'm trying to point out this is what we call conduction. One hits another, hits another, hits another, hits another. In fact, we're busy on time. I guess I shouldn't bring it up, but remember I told you about my son's binder, and he says 10 reasons not to take physics, and one of them says you'll never enjoy movies again. We just did this on Thursday, and he was watching that movie the day after. Day after tomorrow. And I just sitting there watching it on the screen, just having the hardest time. And if you're familiar with the movie, the screenwriters somehow wanted to get New York to freeze, or the whole East Coast to freeze, and they had to do it real quick. And so their answer was what? Let me see the movie. Yeah, the air up here is really cold. So if you bring it down, if there's some magical force that brings it down, it'll make it cold, right? Wait. Now you guys saw this last time. What happens if you take a gas under low pressure and you bring it down to high pressure? What are you doing to that gas? You're squeezing it. It gets hot. And so sure, it's cold up there, but the whole idea of bringing it down, it's going to be warm. So you're still not going to have cold air. So anyway, and the reason that comes back to my mind, fortunately, is there's another dumb movie he was watching. The Congo. You ever see that one? No? Not good. Don't watch it. All right, but this one actually was the flip side of that. So this one was good, and this reminded me of, because that movie centers around this warfare that's going on in the African jungle, and they're trying to get the diamonds from Africa. And why do they want the diamonds? Because they're trying to build lasers, and if you know anything about lasers, their troubles is they overheat. So you've got to conduct the heat out of them. And this is it. And so I actually appreciated that part of the movie very much, because diamond is one of the best conductors of heat. The molecular bonds between them are very strong. And when you hit a diamond on this end, that molecule, bing, 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 hits the next. And the conduction rate of a diamond is really, really strong. So I thought it was pretty clever. I enjoyed that. So that flashed to my mind, and then the other one, and so I don't know why I told you all that story there. But that's the two movies that popped into my mind recently. Anyways, but I want to emphasize, do you get the idea of conduction? That one hits another, hits another. And so now, if we got the how it works, let's do the mathematics of the rate. How quickly does the energy go down this pipe? And I think you can imagine then that the heat per time must be related to what? Well, there's 4 factors. You might be able to kind of catch them out. I would think that you would probably guess a few of these. One of them that is hopefully obvious is the area. I mean, the wider this, and I don't want to use the word pipe, but it is kind of like water flowing in a pipe, but it's not molecules moving, it's energy moving. But in this rod then, the more area you have, the more molecules you have that hit from one end to another to bring it apart. So a rod that is twice as big, I think, would conduct twice as much heat. Fair enough? Makes sense? And then likewise, the reciprocal effect might be for how long is this pipe? What is the length of this pipe? If you've got a rod that is twice as long, then in order for the energy to go all the way down the pipe, it has to hit twice as many molecules, and it's going to take twice as long to get to the other side. So I would expect an equation that looks something like this, where area is in the numerator, length is in the denominator. The other two that may not be so obvious, or at least maybe their symbols not so obvious, is something here that depends on the material itself. And so this is what we call the thermal conductivity of the material. How quickly, if you will, does it conduct down? And that's what I was referring to in the case of the diamond. Diamond works extremely well, and most of your metals work extremely well. The rate of energy conducts, whereas other things like woods and plastics and glasses, this number here is pretty small. So you can imagine that in your book you have a chart that lists all these different conduction rates. Question?
So water is not very good, even though water can hold a lot of heat for mass, it's just not very good conducting either way.
Right. Yeah, and don't confuse how much energy it takes to warm up 1 gram, its specific heat, with how quickly does it move the energy from one place to another. Those are two important and different, although part of thermodynamics still, but different ideas. Yeah.
Can you get K without a table?
Well, you get it by making a measurement, if that's what you mean.
Yeah, can you calculate it or predict it?
I'm sure they do, because there's material sciences like.
Yeah. Okay, so I'll say yes to that, but there's going to be a number of factors that go on. So you would sit down, for example, how strong is the bonding strength between the molecules? That's not the whole story, but you would say, okay, things that are stronger would have a bigger conduction of heat, because when one molecule moves, it pushes on another. So there are individual factors that can be calculated, and then if you grouped all those together, I would think that the theorists could get pretty close to that. Yeah, yeah.
Not to get off on too much of a tangent, but if the molecular bonds between one chemical and another chemical were the same, but if one chemical has larger molecules, would it have a larger like it could transfer energy the same, but it would absorb more heat more quickly because each particle was a larger molecule?
Oh,
it's on a micro.
Well, I would think those with a larger mass would have a smaller conduction rate because of the inertia effect. See, you hit one, now you got to make that start to move, and it's hard to make it move, you know, Newton's second law. Yeah. And so again, I would think that would come into play too, as well as how strong, the bond strength and the angles of them and other features. But most of this is very simply done in a table. You put the material in the lab, which is actually what I want to show you here. So if I take my experiment, here is what we call the conduction meter. And it does exactly that. It measures the rate of conduction. You'll see that I have 5 rods. And I'm going to put the flame right in the hub. I'm essentially warming one end of all 5 rods. And the heat then will conduct out, and the end will start to warm up. The end are pieces of wax. That's what these red things are. And when, of course, the edge of it gets hot, then the wax melts. And so that is the point, is to give you a visual effect of, will the far end of the rod, where the wax is, will it get hot? And yeah, it will. Now, it'll take some time. And this is to show you that it'll be different for the different materials. This first rod will probably go first. This is copper, and copper has the fastest conduction rate of all the metals up here. But as I go around, that's copper, brass, nickel, iron, and stainless steel. And so we have conduction. We have one molecule hitting another. Ooh, I don't know if you can see it dripping, but I was hoping it would fall. There it goes. But it got hot. Started dripping, actually. There it goes. Okay, there goes the brass. And so at least of the metals I have, I can see that copper has the fastest conduction rate. Brass is next. Pretty sure it's iron next and then nickel. But they're really close. So it can vary depending on how I hold it in the flame, but they're a little slower. Hello. Anytime. Ah, there goes the iron. And the nickel should be right next to it. There we go. And stainless steel, we're going to be here till Christmas, so I'll leave that alone. But stainless steel has a terrible, terrible conduction rate for the metals. I mean, it's better than wood or plastic or glass, but for the metals, it's really low. Yeah.
I think you mentioned that diamond has a high conductivity of heat. How would you realistically design a diamond to transfer away heat if diamonds are not that big?
Well, they're not that big and they're expensive, so you don't really use them. No. Yeah, yeah. But they are really nice. And in fact, if you ladies who go to the jewelry store, they will often do that. They've got this little probe. It's got two metal edges, and they'll put it right on your diamond. And the idea is one is hot, and the other is a sensor of when it gets hot. And if you put that down on a diamond, the sensor will pick up heat almost immediately. And you put it down there and it goes beep, real diamond. If it's a fake diamond, you put it on there and the sensor will not go off. It will say, hey, I'm not getting hot. I'm not getting hot. Even though this side is warming it, the heat's not conducting over.
Is that for industrial diamonds or like artificially made diamonds? Like what we use on drill bits and stuff?
Well, the artificial ones conduct pretty good too, not as well because they're not as pure. In fact, you've seen them and they're ugly to look at, you know. But yeah, but so I'm talking about the nature-made million-year diamond. Yeah, they conduct really, really, really well. But the fake diamond, what is that? The cubic zirconium? Yeah. Those don't conduct heat at all. They look really nice and they're to the eye, but you can really pick them up with a sensor very simply.
Isn't heat related to conduction?
No.
Every molecule has to warm up enough for the next one.
Yeah, that's kind of what I was asking.
Go down the line.
Okay. Okay, yes and no. The yes part in what you guys might call the transition state, the transient of the differential equation. But at some point, and so my example here is really, as you said, a combination of specific heat and conduction. But if I come back to this model here, where this is a big bath of water at 100 degrees Celsius, and this is a big bath of water at 0 degrees. When I first put the rod connecting hot water to cold water, then you're right. Then there is a specific heat issue because I've got to warm this up. But after a long period of time, however that long that is, 2, 3, 4, 5 minutes, okay? Eventually, what is going to happen is this end of the rod is going to be at 100 degrees, this part of the rod at 90, this part at 80. You get the idea, and eventually at 0, okay? And now, after that first 5 minutes, after everything's done its specific heat and warmed up, there's no more change in temperature as this sits here for the rest of infinity. See what I'm getting at?
What about the right side though? It's going to warm up.
Well, okay, no. I mean, let's say I don't let it warm up. Let's say I keep piling ice. So this is ice water, and I never let it warm up. This is boiling water. I never let it cool down. This then will never change its temperature, and yet there's still a conduction rate. See what I'm getting at? All right. So there is a conduction rate separate then from the specific heat. But if you allow your two sides to change temperature, then you have an added complication to it, that not only are you talking about the conduction rate of them, but now the energy as it conducts, it may be very fast, but it kind of stops here as it's warming it up. Yeah. And so during the warm-up process, your conduction rate will look a little bit slow because some of the energy is being absorbed to warm up your metal. But like I said, after we reach what we would call a dynamic equilibrium, then that's what I would measure its conduction rate. Yeah.
A specific heat on a heat sink, for example, would give you a nice buffer against processor cycle or something like that.
Yeah. And so I thought I'd show you a couple of other fun conduction ones. This is some neat one. I put some ice in here while we were talking, and it probably doesn't surprise you that if I put a bunch of ice on a piece of wood, it will conduct heat up from the wood to the ice at a pretty slow rate. And it's ice, and it's still ice, and a couple minutes from now it will still be ice, but before today's lecture's over, it will be water. So it has a conduction rate, it's just kind of slow. Here is a piece of aluminum. And if I put a piece of ice on aluminum, the same physics will take place. The heat will conduct up from aluminum. Aluminum has a really good conduction rate. And see the heat already coming up? And if you look carefully, I bet you'll see the liquid form already. And within a couple of minutes, if that long, all this ice will be melted. It doesn't take long. And the plate underneath it is stainless steel. And so we can watch the stainless steel. And it, like that one, is much slower than the aluminum. It is not slower than the wood. It will beat the wood. But not by much. And so there's your different conduction rates. In fact, I'll let you watch that one melt there as I show you a couple other fun ones here. Probably doesn't surprise you too much if I take a piece of paper, wrap it around a piece of wood, hold the paper in the fire, a piece of paper burns. But where it gets more interesting is if I do the same experiment with the same piece of paper and the same flame above the same height, wrapped around a piece of metal, you will notice something different. And why? Yeah, you said dispersing, but I like the word conduction, right? The paper is trying to warm up. It's obviously in the flame. But as soon as it warms up, it can conduct away. The paper is actually thin, so the paper can conduct pretty quickly only because it's thin. Remember, one of the factors here is how thick or how long the heat has to conduct. Then it gets to the metal, and it conducts into the metal, and the metal then conducts it away. And so we never get above that magical 451 Fahrenheit that we need to light paper on fire here. And so the paper, although it looks like I got a little smoldering here, and it's starting to get warm in my hand, and as you said, there is a specific heat. So eventually the piece of metal will get to be 451. I won't be holding it then. But then eventually the paper will catch on fire. But it's a good conduction one. Oh, okay. And so we'll continue on as we watch these. Look at that one melt. But it brings up this question. Can you boil water in a paper cup? That is a hot, hot flame.
Wow.
And the water, notice, is only filled up part way. So what happens to the top part? Yeah, so the top part is going to burn, and I don't think it'll get hot enough to turn into a flame, but obviously have burnt up down to the water line there. And as we are trying to heat up, or trying to burn the paper, if you will, heat conducts through the paper into the water. And then what happens? Yeah, then the water absorbs it, right? And we know the water's not at 451 degrees Fahrenheit, because what's the boiling temperature of water? Well, 100 Celsius or 212 Fahrenheit, right? And so we're going to have to warm up that water first, past 212. In other words, we got to boil it first before this will catch on fire. So yes, you can boil water in a paper cup, and we will hopefully see that real soon. Yeah.
Styrofoam, would it not transfer heat?
Well, now the styrofoam would have a smaller one of these and a bigger one of these. And so the conduction rate would be low enough that what would happen is the styrofoam on the outside would burn away. And it would burn down until it got thin again. Until it got thin enough. Ah, boiling already. I didn't expect it quite that quick, but all right. I guess I didn't have much water in there. And it was very hot. But there it is, and there it is, it's boiling. And it also shows something else here. It shows convection currents, and that's the second one I want to show you. How else can energy be transferred? And so number 2 is convection. Yeah.
But the paper was slightly thicker than the outside of the current, right?
Well, yeah, if you do this, and of course, I deliberately bought these small little party cups or little kids' cup because they are really thin. They are very, very thin. If you do this with a standard paper cup, you'll see the paper walls burn down to a thinner level, and then the water will boil. But the surface of it all blackens because the paper cup is thicker, and the conduction rate isn't quite enough. We've got to get a higher temperature difference. Which, by the way, I guess I wrote that down while somebody was asking a question. The last factor here is, what about the temperature difference? And so, yes, the temperature difference comes into play. The larger the temperature difference, the faster the rate should transfer. So those are my 4 factors. What is the material? How much area do I have? What is the temperature difference, and how much length it is? Okay. One more step, and I'll take a question, is we should, given our brilliant mathematical education that we have, change this really to a higher level math. Let's get away from the algebra and into the calculus. So here's what we're saying is the rate per time is dq dt. And that equals to what? Well, a minus k and a, what's this? Yeah, and I would call that a dt dx, where x is kind of this length or the thickness of the rod, or length of the rod, thickness of the paper, but it's that thickness of where the temperature difference, and so the rate at which energy flows is related to the material, the area of the material, and what we'd call the temperature gradient. How much temperature difference do you get as you move along? Yeah.
Why is K a constant?
Linear.
Well, it's a little bit like specific heat. Is it exactly a constant? No. But it doesn't change over too significantly over normal ranges. So we're working from about 0 degrees Celsius to boiling water, 100 degrees Celsius. It's roughly the same. But the truth is, if you were to measure it at 100 degrees and at 0 degrees, there would be slight differences. Sure. Yeah.
In terms of unit, dq dt would have joules per second, but where do you get the time in? Because when you were talking during the example, I wrote delta t, as in like t2 minus t1 divided by seconds.
All right. So good point. We want the units here, right, to be energy per time. That's a watt.
Yeah.
All right, and we want this unit square meters. We want this in degrees Celsius or Kelvin, and we want this in meters. Means that the units for this must be a watt meter degree Celsius. And again, in your table, you'll see that in the end of the chapter. They've got a nice little table that shows the thermal conduction rates for different materials. And like I said, they do list glass and diamond and wood. So this ice is gone. This does look like it's ahead of the wood. Yay. That is boiling, but large latent heat of vaporization, so it's going to take a while to give enough energy for all that water to be gone. It soon will. And then the paper will burn. I guess I should ask you, should we wait that long and just let it go, or? Okay. Yeah. All right. So, all right. I'll probably have my back to it when it catches on fire, so tell me. The second of the three ways is convection. What is convection? And as I pointed out, the convection is a slightly different process. So again, we should ask this question: how does energy get transferred, and at what rate does it get transferred? I'll start with the how part. I mean, what if you were to take, well, I'll just take a room here, and you were to warm some air in this room. And essentially that's what I'm doing right here by this fire, right? Now that's not my intent to warm the air, but that's happening too. But right here the air is getting warmer. What would happen to that air when it warms? Okay, it will move the molecules faster. When the molecules move faster, they will expand. As they expand, they will be less dense, and if they are less dense, they will rise. So this whole thing will get bigger. It will get less dense, and so the hot air being less dense, that's our Archimedes principle, will rise to the top. And so a combination of thermal expansion with Archimedes principle means hot objects rise. And sounds like you guys have heard that before. Hot water rises to the top. Hot air rises to the top. If you were to stand on this desk and put your hand up near the ceiling, you would probably notice it very warm up there, or at least a lot warmer up there than it is down here. If you've ever changed a light bulb, you often notice that. Oh, light bulb's out. You get a chair, you stand on it, and the first thing you notice as you get up near the ceiling is it's warm up there. Or if you dust a ceiling fan, like anybody does that. But whatever it takes to get to the ceiling, there's a lot of warm air up there. And so that is how energy would get to the top of this building, or the top of this room, is by convection. Notice the difference though. Notice that in conduction, we had something warm and one molecule hit another, hit another, hit another, hit another, hit another. The molecule never went up there. But in convection, what we are saying is these are your faster moving ones, and they themselves actually move. They actually go from here up to here. And so the energy gets transported, but so does the material itself. And so that's kind of that subtlety difference between conduction and convection. That here the molecules move. And of course, here on the West Coast, this is a great illustration because we enjoy this in the summertime in particular, where you have this ocean out here that, as we talked about earlier, has a large specific heat. And so even though the sunlight is shining a lot on the ocean, the large mass with the large specific heat of water means our ocean doesn't warm up. And so maybe we have like our 60 degrees Fahrenheit for our water. Okay, water's gone. So we have our 60 degree water out there. But what's interesting here is inland, the rocks and the sand have a much lower specific heat than the water. And so when that air gets hot, it will rise. And so there's our convection happening inland of California. And if that air were to rise, what would happen then to the air over the ocean? It gets drawn in. And what ends up happening is we get some natural convection currents. We often refer to this real easily as the sea breeze, the afternoon sea breeze. You get up in the morning, if you look at your flagpole out at the pier, no wind whatsoever. By noon, that flagpole can just be ripping. And the reason why is the convection currents. And so the warming and the rising of this air, then drawing this in, is why then Santa Barbara will stay cool, because now this air comes in over the ocean, and so we got this nice pleasant sea breeze blowing in. And so you're here in Bakersfield at 105, 110 degrees, and you're here in Santa Barbara at 65 degrees going, all right, this is why I live here and not Bakersfield. Yeah.
Is Bakersfield particularly inland or a coastal place?
No, Bakersfield's inland.
Okay, because I heard that that's because generally coastal areas are colder than inland. In general, coastal areas are cooler than inland area.
I think a better word is mild, because they're cooler in the summer and warmer in the winter.
Okay, the giant ocean nearby.
Yeah, yeah. So right now with the storm coming in, it's going to be cold in Bakersfield. Why am I picking on Bakersfield? I don't know. Anybody from Bakersfield?
There's Fresno, Bakersfield, Stockton.
Okay, but be real. They're going to be really, really cold right now, and we're going to think about putting on a sweatshirt, you know. And then summer's going to come around, and they're going to be blistering hot. And again, we're still going to be 65. Yeah.
So that explains the sea breeze moving to the right when it's hot.
Oh,
But
yeah.
So if the inland gets cool, wouldn't it go the other way?
It depends how it gets cold. Yes, if it is cold because a storm is moving through, which in our case goes from the west to the east. The west to the east movement of the storm stops it. However, there are other reasons to get cold, especially here in Santa Barbara. Santa Barbara and Malibu are each very famously known for their sundowners. You know what sundowners are? When the sun goes down, what can happen is things begin to cool down. Since the sun sets in the west, the inland areas start to cool down sooner. In addition to that, the inland areas are made out of rock and sand, not out of water, so their specific heat is lower. And so the point is, these inland areas can cool down a lot. I mean, take some time to look at some weather reports at Bakersfield or Las Vegas. I mean, Las Vegas this time of the year is kind of interesting because it gets enough sunlight that daytime it can go up to 75, 80 degrees. And nighttime quickly drop down into the 30s. The lack of a large specific heat around it can have some dramatic temperature changes between night and day. So when the sun goes down over Bakersfield and Las Vegas, this air can cool and sink, and as you said, do the opposite. And the wind can blow out to the sea right after sundown. And so these are what's called sundowners. That air will come rushing through. And if you live near a canyon or a pass of the mountains, that's where it squeezes through the best. And these can be really, really strong winds. More noticeable in spring and fall, very dangerous in the fall, because in the fall not only do you have a wind blowing, but you've just gone all summer without any rain. So now you have dry brush in the mountains with wind blowing to the city. And the Painted Cave fires are a good example of that. 600 houses burned down. 93 Malibu fires are a good example of that. You know, 100 houses burned down. And so when you've got these strong winds and dry conditions, you know, and fire, there's nothing going to stop it. And this is our area. This is the weather pattern for our area, Southern California, the sinking air and warming up and then blowing our Santa Anas.
The other day I was up in the mountains and I was watching like the fog roll in,
Huh.
but it wasn't really like the fog was actually traveling. It was more like it was condensing and then like in stages getting closer and closer to light.
Oh, okay.
How does that relate with convection and conduction? Or is it more of just having a drastic change in pressures, or it's actually causing like the water molecules of the ocean to condense?
Well, okay, so you don't think it was...
Because it was kind of weird. It was later at night. You would think that the wind would be blowing out because of the convection, but it was actually coming in. And I don't think it was like the actual air molecules traveling, more that they were just condensing, and it appeared that it was rolling in.
And the cold air?
Yeah.
Interesting. Now, normally I don't know. That's not normally what I see. Normally I actually see the fog moving in, and the molecules will...
It didn't look like it was really far out, and you couldn't see very much fog. Like it was just being created.
Well, I don't doubt that it could be created, because again, you could have a large air mass, cold air mass, that is moving along. And as it moves to the next one, but the conduction, doesn't seem, because air doesn't conduct that fast. It doesn't seem like it conducted to the next level and made what was already there condense. It seems, maybe it was more gentle and you didn't notice it, would be my guess.
Right.
That the air, which was cold and moist, maybe just above the condensing point as it moved in, then moved condensed. That's my guess. Yeah. Interesting. Yeah. Well, anyways, I wanted to do this one here as one typical example. Another great example is just a visual effect that you probably have seen in your own car. If you go out to your car, and you will probably notice when you open the door that at least on a sunny day, it's not going to happen with the clouds and the storm coming in today here, but when you open your car door, have you ever seen the shadows on the ground? Because what's happening is you are seeing the rising air. The inside of your car is warm. You open the door, and as that air comes out, it's rising. And I know on a summer day I'll do that a lot. I'll go out to the parking lot, I'll open the car door and just go, okay, you know what? I'm just going to open the door for a couple seconds here. I'm just going to let some of this hot air come out. And of course, as it ripples and rises, and you can't often see it, but it will make shadows, you can see the turbulence on the ground.
Is that also with refraction?
Yeah, so what's happening is you are seeing the effect of our optics, our refraction on the light, which, by the way, is our next unit. So after spring break, we'll talk more about this again, that the light is refracted differently because of the different density of the molecules. So even though my eyes can't exactly see the molecules, the light is affected different by them, and I can see that in the shadow on the light. Water heaters is another good example. As I was getting ready this morning thinking about this class, I said, oh yeah, here's this water heater one example again. Is because my water heater was, warming water all night and keeping it warm. Where's the hottest water in the water heater? Yeah, and so this is really hot. Why did the engineers put the flame at the bottom of the water heater? Because where's the coldest water in the water heater? Yeah, now, assuming nobody's used any hot water yet in the morning, I would think it's pretty hot all the way through, but it's probably the hottest up at the top, and it's just kind of warm near the bottom. And again, fortunately, the engineers were smart enough to say this is the hot water that's going to go into the house. This is going to go to the shower and the dishes right here. You're going to siphon the water off where? At the top. And so I get in the shower, I adjust the knobs, and I said, okay, this is just right. I have a little bit of hot water and a little bit of cold water coming into my shower. Nice balance, just right.
Cold water come in the bottom.
So now, as I use the hot water, I have to replenish the water that came out of the hot water. Where does it go in at?
Bottom, I guess?
Yeah. And again, fortunately, the engineers are smart enough to put it at the bottom. Why the bottom?
Well, that's where the cold stuff is.
All right. And so they'll have a pipe. And in mine, it actually enters the top, but there's actually an inside tube that brings it all the way down to the bottom. You wouldn't want to let it out right here. Why not? Yeah, it's going to circle around and mix with the hot and end up in my shower right away. And it won't be hot. But what will happen is as the cold water comes in, it will begin to fill this up. And so even though cold water is now entering the water heater, I don't get any cold water into my shower. And so they've used these convections to separate the hot and the cold water. And I will notice maybe partway through the shower that it's not as warm as it was when it got started. Because I have used all the top water, which was really hot. And now the water that was in the middle of the water heater is now going to my shower. And that wasn't nearly as hot. So I adjust the hot water knob about halfway through my shower. I don't know if you do, but I go, you know what? It's not as hot. I'm going to turn it up just a little bit. Now it's hot again because I need a little bit more hot water because I have the lukewarm water. And if you stay too long, besides getting yelled at by the rest of your family, it will get cold and you will have nothing but cold water coming in, and then you will definitely get out. Yeah.
Haven't they gotten better with what you said with the tankless water heaters? You don't have to worry about all that?
Well, there are tankless water heaters. I don't own one, so I have to worry about it. I need a better paying job, I guess. Yeah.
No, but I mean...
Oh, I know. I need one of my students to become rich and famous and so appreciative of the beginning education that they'll buy me a red Ferrari and fix up the room here a little bit. Yeah. Well, yeah, the tankless water heater is pretty straightforward. It's a giant rectangular box that just has a massive flame in it. And the water comes in and goes out. And the whole thing is just flames of burning gas until the water comes in cold and exits hot. And you know, that's the idea here. So you never run out of hot water. That's the good thing about it. And another really good thing about it is you only are running the gas when you need the hot water. So unlike a water heater, when you go to sleep at night, this thing turns on and it's, say 12 o'clock at night and it warmed the water. About 2 o'clock in the morning, the water's cooled down a little bit, so the flame goes on again. And so you're constantly rewarming that water, and that's the negative thing. Of course, these take a lot of gas. And so you have to have I looked in it for my house, and I needed a 1-inch gas line, and I don't have that. And so the expense of doing a whole new gas line, and in my case, just the way the gas line comes in and the water heater comes in, plus this takes a lot of oxygen. So you have to put it on an outside wall, put a hole in the wall so the oxygen can come in and go out. So between the oxygen and gas it needs, the expense of putting one in is pretty expensive. So
instead of having a water tank, why not just have a gas tank to store the gas so you don't have to have such a bigger tank?
Well, that's an interesting idea. So I could have a big tank of gas. I wouldn't have to redo the lines. Doesn't sound safe. I don't know.
It's not worth it.
But I guess we have big tanks of propane, so maybe that's not unreasonable. But a big tank of natural gas in my garage, I'm a little worried about.
Those are more efficient as far as the amount of gas you use every month, right?
Yes, because they're not constantly rewarming. Yeah. It kind of depends on how you use your water, but in general, these are more efficient. They use a lot of gas at that moment, but they only use it at that moment. They're not constantly warming and rewarming here. But these can be pretty efficient if you start wrapping them in lots of insulation materials and you live in Santa Barbara where it never really gets that cold in your garage anyways. So when I did my math, the extra expense here did not justify the cost savings here. So now that was a few years ago. It was 2006 when I walked out one morning and my water heater had ruptured and my garage was flooded with water. And so I gave this a lot of serious thought. These are nice, but when I figured out the cost of this, and these are, and part of this is this takes a professional install. These are easy to do yourself, so that cost alone just, you know, was thousands of dollars difference. It was like, okay, I'm just going with the old-fashioned tank one for this time again. So that was 06, so that was 6 years ago. So I don't know, maybe another 4 years I'll be in the market again. Yeah.
When you adjust the knob of the shower, what is it doing?
You're adjusting the rate of hot and cold. How much hot? Yes. Yeah. So the cold water would be coming just straight from the service line from the street. So it comes in the street, in from the street, warms up, and then to the shower. And so just like you're washing your hands, you know, you adjust the hot and cold. That you can handle all hot. I can't handle it all hot, but yeah. Well, wanted to show you this before I get too sidetracked on this, but we brought the hot water purposely for this. If you were wondering what these little colors out here, red for hot. So, if I take our little coffee maker here and fill it up with hot water, almost to the top, just so I don't burn myself, but I'll top it off. So there is hot water. Also, this will be hot water. So the other red one will be hot water too. And again, a little bit of cool water, not to cool it down, but just to top it off so I don't burn my fingers. Okay, but that's some significant hot water. Probably wouldn't surprise you to watch hot water. Messed that one up. Try it again. Hot water on top of cold water. Because the hot water is supposed to rise, and the hot water is already on the top, right? But what if I put a little different here, and I start with hot water on the bottom? Do you notice anything different here? No, you don't?
The one with the color red. I mean, clearly.
Okay. Anything yet? Are you guys playing with me or not? Do you notice it now?
All your students are colorblind.
I'll turn it that way. But I'm hoping you're seeing this turn pink. I hope you're seeing this is not clear like it was a moment ago. And that what's happening here is the hot water is rising. The cold water is sinking. This is going to be in thermal equilibrium within a minute. This is going to stay hot here and cold here for a very long time. There's going to be a separation. In fact, the separation of the convections in water is often a lot more than the conduction rate. So the water staying on the top is normal. If you've ever gone into a swimming pool in spring or fall, and maybe even summer, you will notice that. Where's the warm water in the swimming pool? It's on the top. So it's you go, I think I'll go swimming. I wonder how the water feels. And you put your hand and you go, oh, that feels warm. I can't wait to go in. And then you dive in and you realize that 3 feet down, it is cold. And so there's the separation. And lakes are the same way. You know, where's the coldest water in Lake Tahoe? And maybe that's probably not a fair statement either, because water gets more dense till 4 degrees Celsius. Then as it starts to freeze, it gets less dense. So I guess I should be careful. So the bottom would be 4 degrees. Once you get colder than 4 degrees, the crystals start to form and it starts to get ice. And we know ice floats, so we know ice is less dense. And so then it starts to rise again. So if the lake doesn't go below 4 degrees, so I should have picked on Lake Cachuma. Where's the coldest water in Lake Cachuma? at the bottom. It's probably not 4 degrees at the bottom, but it is the coldest waters at the bottom and the warmest waters at the top.
Well, if water's under a lot of pressure, like really low depths,
Yeah.
wouldn't it, I mean, couldn't make it really cold even below freezing and not freeze?
Well, oh, I see. Because the pressure is so great. Yeah, could. Could.
Yeah, you just have to have the pressure greater than the
Yeah.
pressure of the ice crystals could withstand.
Yeah, so I guess the physics answer is yes. The number, though, I don't know how big that is. How deep is that?
Right.
Yeah.
Probably not like as deep as a lake.
Yeah, probably not as deep as a lake, but it makes you wonder about the Mariana Trench. Yeah.
Tahoe isn't it like 5 miles deep?
And 5, ooh.
It's really Tahoe's not.
Tahoe's deep, but I can't imagine it being 5 miles deep. I'd be surprised.
Maybe I was 5,000 feet. Is that right?
Okay, a mile. That would make, because, well, 5 miles, I mean, the mountain's not even 5 miles high.
Yeah, you're right.
5 miles, yeah. 5,000 would make more sense. All right, well, anyways, convection, as long as we're here, you guys asked a couple questions about these. What are these? These are heat sinks, and this one happens to be pulled off an old electronic device here. There was actually a power transistor mounted here, and then this was mounted, say, on the back side of the amplifier. But here's the idea. Notice it is made out of aluminum, and notice it is mounted in this way. And in a second, notice also it's black in color. So that's the last piece of the puzzle here. But the idea of it made out of aluminum then is if you were to mount this on a piece of electronics, if the idea is to get the heat to conduct out of the electronics, that's what the aluminum is for. You saw how quickly the aluminum conducts. And so as we bolt it onto something hot, it will conduct the heat into this piece of metal very, very quickly. Then why mount it this way and not this way? This is the convection, right? Because now, with these fins out here, what we call cooling fins, the air between them is going to warm up. And when it warms up, what will it do? Yeah, it will rise. Mounted this way, it can't rise as well as when it is mounted this way. And so the engineers have taken advantage of these natural convection currents that it will rise, and then more air will come in. Most of your electronics, even if they're not this much power where they need a heat sink, will have holes drilled in the top and the bottom. What are the holes for? Yeah, we call them breathing holes. But the electronics there, say this is your DVR, you want the heat to come out of the box and to rise. And then, of course, underneath, you want to make sure you've got the little rubber feet under there so the air can get under the box and go in. So cool air can come up underneath, warm air can rise. If you put a pretty plant on top of it, you block the airflow. Now your DVR runs a little bit hot, could break. If you put your DVR on a soft, fuzzy towel because it looks pretty, again, you can't let the air get in there. And so those holes are there for a reason, and so let them breathe. Question?
How much does it being black really help?
It actually helps quite a bit. That's the third step. So the black we will add in just a second here. That's the radiation cooling, the third and final effect. Yeah.
So if you wanted to cool the inside of a box or a case, would you want to have the fans pointing in or pointing out?
Oh, now if you're turning on the fan, then you're getting the airflow in a much larger volume than you would by natural convections. So
You want to have high pressure inside or low pressure?
You'd want to have one facing one way, one facing
yeah, you could get, I don't think there's a standard answer I can give you for which way it is. Both would work. And where it is mounted in connection with the holes is what you would want. For example, you're going to get the most volume flow near the fan. Okay, so if this is a microprocessor, and the old microprocessors didn't have fans on them, the cooling fins were enough. And you just mounted them on your PC board. They had fins sticking up, and they would heat the air would rise, bringing more air in. Today's microprocessor, you gotta cool it with a fan. Do they all have fans on them? No. No? Okay.
Most of them do.
Most of you do? Okay. But if you put a fan directly on it, then you would blow directly on it and away from it. And in that sense, I would think you would want cold blowing in, because I want high volume on a little space. Okay? Having a fan blowing out of my case makes a lot of airflow outside of my case. What it does is let a little bit of air come in every hole. So blowing out is a way of cooling many things, is what I'm getting at. And so if I have many things that don't need to be directly cooled, I would think blowing out would be my choice. Blowing in and directly on something if I want that one object to really cool down. Blowing in, yeah, blowing in. And most of them have both. I know mine has both. It's got one sucking the air in and one blowing the air out, and then one on the processor. Yeah. Which is why dust inside is so deadly on your electronics, because it coats it in a non-conducting material. And so statistics after statistics have showed those who put their computer tower on the floor versus on the desk have a larger failure rate, because all the dust that it brings into the box then coats the electronics, then reduces the conduction for the air to pick up the heat blowing on, and that box runs a little bit hot and then is in danger of having problems. Well, one last thing, I better move on, and probably the hardest thing to explain at this level, fortunately also one that we're going to probably spend the least significant discussion time on, because it has nothing to do with molecules. Did you catch this so far? Did you catch that conduction and convection had to do with molecules? So outer space with no molecules around. You put a space shuttle, a satellite. How do you cool down the satellite? How do you get rid of the heat out of the International Space Station? All that electronics that's running. All those human bodies in there. And the last piece of this puzzle is really kind of asking this. How does the sun transfer its heat from it to us? Are there any molecules between the sun and us?
Very few.
Okay, very few, right? And so what we say then is this last effect is a radiation effect. This, like I said, is a little hard to discuss at this point. It'll make a lot more sense near the end of the semester. But we say the energy is transferred not by molecules at all, but by electromagnetic waves. Now there's a big word that will hopefully means a lot to those of you who've already gone through Physics 122. Maybe very little for those of you who haven't quite yet. Maybe I should put it and just say light waves. Another category of light waves or electromagnetic waves is what we call IR, or infrared radiation. And each of those terms you might have heard, but these are waves that are traveling through space. They are not made like sound waves. They are not made out of atoms themselves. What is waving is electric and magnetic fields. And so, like I said, those of you who had 122, I think this will mean a lot more to you. But if I take something like the sun, and the sun is hot, so the atoms are moving. And remember, the atoms have charge. And the charges in there are made of electric fields. And so what will happen is they move around. As the atoms in the sun move around, they make an electric field. That electric field makes a magnetic field. That magnetic field makes an electric field. That electric field makes a magnetic field. Electric, magnetic, electric, magnetic, electric, magnetic, electric, magnetic. 93 million miles away, here's Earth. And Earth gets hit with this electric and magnetic field, hitting the atoms that are, say, in my body and making the atoms move. That is heat. And so, again, like I said, the process is a little difficult to discuss because we haven't really done, or at least not all of you have done, electric and magnetic fields. But this is what is meant by radiation. Energy transferred not through molecular motion, but through electric magnetic waves. Your cell phone's the same thing. You get information or you send information by an electric field. There are no molecules that, you know, are taking the information from your phone to the next phone. Now, it started as movement of molecules because you talked into the phone. Hey, Bob, how you doing? Those movements turned into an electric field. That electric field went through space and was picked up on the receiving end. That's a form of energy. And so that's why, like I said, this one is hard to really predict. So I'm going to tell all of you, think of these as light waves. That's probably the best thing I can say. Light waves is a narrow band that the human eye can see, but electromagnetic waves all carry with it energy. And anything that has temperature, anything, and we'll go to the sun is just so hot, a fire is so hot that the molecules move so fast that they vibrate at a rate that our eyes are used to. But what about this pen? Does this pen have atoms in it? Are they vibrating? So are they giving off electromagnetic waves? Yeah.
With the color red.
And that's the hardest thing to get across. They are giving out energy. This is like a light bulb, but you can't see it. You've got to warm it up. You probably saw that earlier. Does this give off electromagnetic radiation? Yep. Can you see it? No. If I make the molecules move faster, could I see them? Yes. And so just simply making them hotter, they will glow red. There it is. Now they're hot. Now they're vibrating in a range my eye can see. But I want to emphasize to you this same process, whether it's hot or cold, gives off radiation. It may be part my eye can see, like a hot fire or a hot piece of metal, or it may not. Yeah.
So electromagnetic radiation is on the spectrum. So like from our cell phones, it's radio waves. From this, like infrared, it's like what's common in heat, and then we have X-rays. So, would my cell phone's radio waves, or would strong enough X-rays be would they heat up the matter inside my body if they was focused on me, or would only infrared rays heat up the molecule? Because I know how like a microwave works, where it only heats up, or it only adds energy to molecules of a certain size. That's why it can heat up water, but with other things it won't.
Well,
with metal reflects it. And
okay.
There's other stuff, but will other ends of the EMF spectrum heat up stuff like higher?
Well, okay, so yes, you kind of answered your own question. Is there's this whole range of waves,
Yeah.
and if your material can absorb it, you are changing it from electromagnetic energy into heat energy. So you and other materials don't always absorb everything. So infrared pretty much gets absorbed really easy by all materials, so we call that the infrared heat because it really goes to heat. But if somebody were to shoot X-rays at you, if your body were to absorb that, it would turn to heat. If your body doesn't absorb it, it doesn't turn to heat. So if you've ever broken an arm and gotten an X-ray, most of them go through. Some of them do get absorbed. Some of them, and those that do get absorbed turn into heat eventually. So yes. Glass is an excellent example. Greenhouses are built out of glass for just that reason. They let visible light go right through them. They don't convert it into heat. But they absorb infrared. So, when you make a house out of glass and the sun comes up, or in our case, a car parked in the parking lot with glass windows, when the sun comes up and shines visible light, it goes right through the glass to the interior materials. There it's absorbed, turned into heat. As that gets hot, it wants to re-radiate that in the infrared. Can't, because the glass absorbs it and the inside of that greenhouse or the inside of your car can get very, very warm compared to something next to the car that doesn't have a wrapping of glass around it. Yeah.
So is that the same thing as nuclear radiation?
No. Yeah, and be careful with the word. I think the word radiation just scares people off the ends. It's like, oh, this is going to cause cancer and kill everybody. But just like your cell phone puts out radiation, we don't think it causes cancer. I guess we'll find out soon.
Nuclear radiation is like a very specific kind of...
No, there's
Well, nuclear radiation then comes in 3 flavors also. There's an alpha, beta, gamma. The gamma part is like this, but not the alpha and the beta. The alpha and beta are actually subatomic particles, protons, neutrons, electrons, that are shooting out from the nucleus.
So that's the one that gives you superpowers.
Yes, exactly. Right. So this is the gamma radiation. So the gamma radiation is frequencies higher than the X-rays, and really aren't absorbed by the human body. Yeah. I mean, well, maybe freeze it. Yeah.
So radiation is caused by the molecules moving really fast and then they create magnetic,
Right.
electromagnetic waves.
Right.
So if things are at absolute zero, they can't give off any radiation.
Correct. I'm glad you say that, because then, without proof, we will discover something by Stefan. We will prove it at the end of the semester as we get into a little more of these electromagnetic waves called black body radiation. But Stefan noticed exactly what you just said here, that how much power is given off is going to be related to the temperature. Now, I think what might come as a surprise is it's related to the temperature to the 4th power. Again, near the end of the semester, hopefully that will make more sense. But it answers your question. They said, well, what if you're at absolute zero? Well, on the Kelvin scale, absolute zero, how much power radiates? 0. And so the power that radiates increases, and it's to a 4th power. So you go from, say, room temperature, which is somewhere around 300 Kelvin, just 25-ish Celsius, and you double 300 up to 600. Now that's still pretty warm. That's 300 degrees Celsius, but that's still a lot lower than this metal piece. This flame here was probably warming this up to near 600 degrees Celsius. Okay, but just if I go up to 300 degrees Celsius, okay, or 600 Kelvin, that's doubling the temperature. How much more power is put out with electromagnetic waves? Well, if you double this, but it's raised to a power of 4, 2, 2, 2, and 2 is 16 times, right? So 16 times more power. So it's amazing how much power things put out. And I think that's, again, why at room temperature, we don't think about things putting off radiation. I don't stand near this wall and say, ooh, cozy warm. I can feel the radiation coming from it. But it is sending the radiation to me. So I wanted to keep that in mind. And maybe not a surprise, how much total energy would depend on how much area you have, how much surface area. So it's not only what temperature, but the surface of this thing, because radiation's coming from every square centimeter. And so more square inches, it makes sense. The other 2 things are labeled with a sigma and an E. The sigma is the constant. This was discovered first by Stefan, and later on we're going to calculate by Planck. But let's just call it Stefan's constant. He's the one who measured all this radiation and said, okay, how much comes? And he used units of watts and meters and Kelvin and said that's our material. But there's one more factor that probably is the hardest one to grasp. The emissivity here is really saying how well does it emit. In other words, it is a factor that can be anywhere from 0 to 1. how well does it give off its energy? And I'm going to switch this for a moment. This is also saying how well does it absorb. Let's go back to the sunlight to see if this makes any more sense. When you walk outside on a sunny day, do you put on a white t-shirt or a black t-shirt?
I always wear black.
It kind of depends what you're trying to do, right?
Are you in Alaska?
Okay, right. So doesn't a black and a white t-shirt have a different effect on the sunlight? What would you say about a white t-shirt? It reflects, right? What would you say about a black t-shirt? It absorbs. So looking at this number, not as the emissivity of it, but the absorption of it, I would say a black t-shirt fits in this category of 1. The black t-shirt absorbs everything. The reason it's black is if you shine red light on it, what happens to the red light? It gets absorbed. That's why the shirt looked black. You don't see red coming from it. If you shine blue on a black t-shirt, green on a black t-shirt, all of that gets absorbed. And so we say all the energy gets absorbed in a black object. What about the white object? Or a shiny, polishing, silvering object?
More of it's reflected.
It's reflected, right? And in a perfect world, we'll say all of it. Obviously, nothing really happens with all of it. But in that case, I would say this number is closer to a 0. And a perfect reflecting object would be 0. It doesn't absorb anything. That's why we call it white. We call it white because if you shine all the colors on it, red, green, blue, orange, they all reflect. Fair enough? And so this is really a property of the material, the pigments that are made there, on which colors they reflect and why they reflect them. So the same thing works in reverse. If something is black and it absorbs everything real easy, then it also emits very easily. You asked earlier, why did we paint these heat sinks black? Because, what does that mean? Yeah, they are going to radiate this out very well. If they were shiny, what would they do? You might say it would reflect it back in. Because let's take this analogy of you in a t-shirt outside. Now take you in a t-shirt inside. So instead of being outside where the sunlight is hitting you, you go inside. And just to make it interesting, you shut off all the lights and turn on one little light to play your video game there. There's not much radiation there. Are you going to be warmer in a black shirt or a white shirt? Now maybe I should have asked that outside. I think you know that. You're going to be warmer in what color shirt outside? Black, because you absorb the sunlight. Let's go inside. You're going to be warmer in a black or a white t-shirt inside?
Why? Because it reflects back on radiates black.
Yeah, there's a different issue here. It's your body's own radiation. Don't forget that. When you were outside, you were absorbing the Earth's, the sun's radiation, but your own body's radiation coming from the inside out, hitting the t-shirt, got absorbed too. If that t-shirt had been white, what would it do to your own body radiation? Reflect it back. So that white t-shirt has the advantage of sending the radiation back to you. But the sunlight is so much more energy that it's well worth giving up your body's radiation to absorb the sun's radiation. But what happens on the inside? The inside, your white t-shirt's going to keep you warmer. It's going to reflect and hit the white and come back to your body. You don't have any black to, or any outside source to absorb. Oh, a bunch of questions, yeah.
White t-shirt under black t-shirt, how effective would that be?
Oh, yes, and my understanding is if you live in places that are cold or hot, you know how to dress well. So a white t-shirt under a black t-shirt is great on a cold day, right, with the sun up, because the black is on the outside absorbing the sunlight, the white is on the inside trapping your body heat in.
And vice versa for the...
And you flip it, right, in the desert where you have the black on the inside and the white on the outside. Yeah, yeah.
How significant is it? I mean, as far as
Well, again, us in Santa Barbara don't think much about it, but my understanding is those nomads of the Arabian desert who still go around on the caravans, they survive because they know this ancient trick. They know where the water source is. They put up their tents. They are dressed in black with white wrapped around them. So most photographs you see of these Arabian nomad people walking around in the desert, they're dressed in white. But underneath they've got black. And when they go into their little portable tent and they take off all the white, they're dressed in black. And you don't usually see the pictures that way. But they're trying to keep themselves cool. And I guess it's a cultural thing. I mean, Southern California, we just take more clothes off, you know. And, yeah. Pretty soon we're down to our bathing suit or less, and, depending on who else is in the room, I guess. Yeah.
You put just the left end and greater sign, but not the equal to sign.
Oh, okay.
Like, there's Einstein's black body thing where he came up with the idea of like a perfect black body where it totally radiates all of its energy.
Oh, right. But it's ideal. There is nothing that's perfect. So the equality sign is more of a theoretical discussion of what could happen in a perfect world versus what really happens.
And then also, I'm kind of confused. I got confused on between the black and white. Does black, like the black heat sinks, does the color also allow it to radiate off more heat?
Yes.
And not just reflect less, but
and radiate.
photons really do send off more photons.
Yeah. Yeah.
Since they're blacker by nature.
So again, I probably did not do it justice because I can't really tell the end of the semester here. But what I am trying to say is I think you could understand how black absorbs more than white.
Okay.
I'm saying the reverse is also true without much proof, except I'll run this experiment to show you that
Conductivity of like metals versus wood. Metal can absorb a lot and release a lot. Wood doesn't.
okay.
It's kind of analogous like that, but it has to do with.
Yes, but it doesn't have to do with,
It's
it's analogous.
absorption and
Yeah.
heat.
It's not conduction,
Yeah.
but it is analogous. Yes, sure, fair enough. Because I want you to see this one. This might surprise you a little bit here. I've got two test tubes. One is purposely black, one is purposely shiny. I will fill them with hot water. Which one will cool faster? And you might be surprised, because again, we often think of the reverse. We think if you put cold water in here and turned on a heat lamp, which one would warm faster? Well, the black one, right? The black one would absorb the radiation and the silver one would reflect it off. And that's what we often think, and that's true. But when you take the heat source from the outside and put the heat source on the inside, so I have hot water on the inside, what happens to the radiation from the hot water on the inside as it tries to get out and hits the shiny surface? It gets reflected back in and it gets trapped in. And this one's going to have a hard time cooling. It has a hard time warming because it reflects this away. It has a hard time cooling because it reflects it back in. And so watching these two cool, I've got two thermometers here that are hopefully calibrated the same. Oh, they're not. 19 and 20. And we're off a little bit there, so I'm hoping this will somewhat work, but maybe I will start by first kind of filling the test tubes with hot water, kind of what I'll call pre-warm them. So now they're already hot and the water cooled down a little bit already. So now I'm going to start with some new hot water, and so I will fill this with hot water, and I'll fill the other one with hot water. And I don't think I did a very good job getting equal amounts of water or preheating them well, so they may not start at the same temperature. But even without at the same temperature, I think we can see a difference between them. And that's what I want you to see here. So this one's 72.7 and this one's 73. Oh, maybe that's good. So this one's a little bit warmer. The scale was also off a little bit too. But I'm claiming that that one's going to cool faster. And if it cools faster, it will catch that one. Oh, already has. And it's now surpassing it. And so there's our rate of cooling. Yeah.
So there's nothing to do with conduction then?
So I'll expand. Is there any conduction here? Okay, great. There is some conduction and convection, but hopefully they're equal between the two. And so the difference between them is all radiation. But there is conduction, there is convection, and there's radiation. But given the same size, the same shape, the same design in the same room, the convection currents and the conduction should be the same. And so I'm really comparing, hopefully, just radiation. They are slightly different surface materials because this one I've painted black and this one I didn't. But that aside, hopefully it shows enough that there is more radiation. 67. Yeah, that's over a degree lower, and like I said, we'll just let it run through and finish. All right. Well, those are the three categories, and I only wanted to talk about an hour for that, but I guess I'm 20 minutes over. Let's jump into some example problems. Let's see how many I can do, and particularly one of these tough ones. And if we run short on time, well, we'll just pick it up on Thursday then. But there is some neat math I want you to see, especially with the work and the energy stuff we've been doing. So the first example I'm thinking of is probably the easiest one, but it's worth doing. It's number 17. It doesn't have a picture, but I will put the computer to warming up while I do this one, and then the next one I want to show you the picture here. But let's look at number 17. Number 17 says this. It says, take 1 kilogram block of copper at 20 degrees. So room temperature. I got this 1 kilogram block of copper. So it's probably about this big. And it's all copper. All right. And we drop it into liquid nitrogen. Now, I don't know if you've ever seen liquid nitrogen, but if you know that nitrogen is in the air around us, it is a gas. And like any gas, if you get it cold enough, what's going to happen? It's going to turn into a liquid. In other words, it has a boiling point, and that boiling point must be colder than room temperature. In fact, it goes on to say here, the liquid nitrogen is at 77.3 Kelvin. How many grams of liquid nitrogen boil away in order for the copper to cool down to 77.3? This is a great experimental tool on how do you cool something down. Well, just put it in a liquid that's cold, right? Now, the problem with putting it in a liquid that's cold, though, is the liquid can warm up. Unless what? It can't get warmer than its boiling point, right? And so when you have a liquid at its boiling point, it doesn't get any warmer. When you add heat to it, what happens? It boils away. So a good way of getting something cold is to take a liquid that is already cold, in this case liquid nitrogen. So I'll put nitrogen here. And I know that it's at 77.3 Kelvin. And what I'm going to do then is put a block of 1 kilogram of copper in to that liquid. And here's what I know. The heat that goes into here, and so I will say nitrogen plus the heat that comes out of the copper must add to what? Yeah, 0. Why 0? Right. Remember our positive and negative signs? And this was one of many reasons I grabbed this one. When energy goes into something, is that a positive or a negative number? It's positive, right? So the heat going into the nitrogen, this should be a positive number. But what about the copper? Heat comes out, so that should be a negative number. And how should these compare in magnitude? They should be equal. Why? Conservation of energy, right? So no work in this problem. This is all just heat energy. Heat in equals heat out. And so those two should add up to 0. So I will start with the nitrogen. The nitrogen is already warmed up to its boiling point. And all it does is boil away some nitrogen. And so this would be MLV, right? And so take us back to last week, actually I think last Tuesday where we get started. One of the formulas for counting heat when it changes phase is this: the mass that changed phase times the latent heat of fusion. And that's what we're after right there. The mass, and I should put nitrogen down here. A V. Yeah, V for vaporization? Oh, if I said fusion, I'm sorry. But it is vaporization, yeah, because we're going from a liquid into a gas.
Are we assuming that this whole thing happens instantly?
No. No, this could take time. But the amount of energy is still the same, right?
So doesn't the air temperature matter?
Oh, okay. Fair enough. So we've got this big insulated vat, and yeah, so this whole liquid nitrogen. Yeah. Okay, back to the movies. Oh, this was really good. Do you remember how the Metal Man in Terminator 2, 3? It was 2, wasn't it? Yeah. The T-1000. Do you remember how then our governor, right? How he. It was brilliant. He's on the motorcycle going down the freeway. He goes, everything I've done to this liquid guy, I've shot him with a shotgun. I've hit him with a sledgehammer. All it does is make the liquid deform, and then he forms back. How can I crush this guy? And what clicks in his head? Did you see what happened on the freeway? The truck driving next to him was what? Liquid air. It said liquid air on the side. It was liquid nitrogen. And so if you miss this on the movie, he goes, that is liquid nitrogen. That is cold. If I put liquid man in liquid nitrogen, what's going to happen to liquid man? He's going to turn to a solid. And then what could I do with a solid once I shoot him up? He breaks into billions of pieces. So I really like that part of the show. I was like, oh, that's it. He's gonna, I know, he's got it. And he does, and he shoots it, and he blasts the guy into little pieces. I thought the show was over. Then it just got better. Then all the little pieces warmed up. And when they warm up, they become a liquid. Now, I don't know how they all kind of flowed together, but then they all flowed together. Magnetic pieces, there you go. And they all kind of flowed together, and then the movie continued here. But that's what you'll see this a lot on the truck, on the freeways. You'll see this liquid nitrogen. I see a lot of it going to UCSB. Makes sense. They're doing a lot of research there, and I just, seems like every morning I see a big liquid nitrogen truck on its way up, delivering from Los Angeles on up to UCSB here, and so. Well, they have these giant, the thermos we used to use, the container was literally this wide. It was on wheels, and we'd wheel it into the lab, and it's just a giant thermos. It really is this wide, and it's all insulating material, and the liquid nitrogen is only in something about this big. And the reason is for that is because you don't want this to warm up very easily. And so we just wheeled it off into the lab, and you would fill up your containers with liquid nitrogen constantly, running your experiments. And you would use it up, and the room would warm it up, and it would boil away. So within a few days, you had to get another shipment. So that's why the truck comes up every day to drop off a shipment for a lab or two. Yeah. And so All right, so but back to the math here. So here's the mass, and this is what we are. This is actually a latent heat of fusion discussion here. And so I will put that here. This number I need to know. This would be the MC delta T. That has to equal 0. Well, let me put in my numbers here. The unknown is right here. How much mass of nitrogen boils away? The other numbers are actually given. I didn't get a chance to read them in the problem, but they do say that the latent heat of vaporization of nitrogen is 48.0 calories per gram. So this is 48.0 calories per gram would go there. They also say the specific heat of copper. The specific heat of copper is 0.092 calories per gram per each degree. So I will put in my copper's mass in grams. They said it was 1 kilogram, but they also said this was 0.092 calories per gram per each degree Celsius. So to get grams to cancel off, I need to make sure that's in grams, and then that's going to be in calories. And the change in temperature, that one, maybe I'll give myself a little more room here. That one is hopefully a little straightforward because, again, I am starting at 20 degrees Celsius, which is 293, oh, no degrees, sorry, 293 Kelvin. And so my change in temperature is final minus initial. Now look at this, final minus initial, positive number or negative number? Negative, right? Which is good, because which way did the heat come from? Didn't it come out? So I want this to be a negative number, yeah.
So that liquid nitrogen is not going to change temperature.
Right. Right. And the key here is this is liquid nitrogen, it is at its boiling point. So just like water. You get water up to 100 degrees, when you add more energy to it, you don't warm it above 100 degrees, you just boil some water off. And again, that's why this is a neat technique. Liquid nitrogen is very cold, and it's not, well, too expensive. I mean, we don't buy it here at the community college, but for a university or a research center, and you know, Raytheon research right there too. So that truck is constantly going to UCSB and Raytheon, just tons of nitrogen. It's, you know, it costs about the same price as milk, you know, a couple of dollars a gallon. It's very reasonable. On the other hand, if you really want to do an experiment that's really cold, you can buy liquid helium. Now, benefit of that is this is only 4 Kelvin. Disadvantage is it's going to be extremely expensive. So, what you
get down to the
a liquid hydrogen's explosive. So nobody, yeah. So just like we don't, we don't mess with liquid hydrogen. Yeah.
We know that it's at the temperature of its boiling point, but how do we know how far through the stages? Like how close is it? We're just assuming that it's just at the very beginning of the transition phase.
Yeah, they tell us the boiling point, and maybe I didn't read it enough here for you, but it says liquid nitrogen at 77.3 Kelvin.
Because it could be almost boiling before we start.
Right, and it's actually when you do this, it's already boiling. I mean, you put it in a container and you put it on the desk and it's boiling. Because it is warm, it is warming because of the air from the room. Now, then I throw this in and then it really boils. So this is the extra mass that boils compared to if it was just sitting in the room.
I'm saying when it goes up like this, it goes flat and then it goes up again.
Well, it doesn't go up.
The flat part right before it goes up in temperature.
No. The flat part you're talking about is a graph of energy, not temperature.
Right. So we could be at the moment just before it boils. So our LV would be 0.0001.
No, I think you're missing something in the picture. The temperature, when we did this graph of temperature versus energy, or versus time, as we were heating it up. And it went from here to here. The reason it started going up to here is because we had gotten, how can I say this? It'll only go up to here when it all boils away. And it can't start warming up until all of it boils away. So it doesn't matter whether I'm in here where only some of it has boiled away, or here, as long as, and maybe this is what you're getting at, as long as I still have enough that when this cools down, it hasn't all boiled away. Does that make sense? So if I have a big bath of this, that's all I care about. And so I'll put this in, and I'll just let it sit there for 10 minutes and pull it out. And it wouldn't surprise me if many of you, when you transfer, you will be doing experiments like this. This is extremely, extremely common. There's not too many people who finish an academic career who don't, well, maybe I should say a science career. Many of you will go into engineering or mechanical engineering, so maybe you won't do this. But you know, liquid nitrogen, must have done it a million times. Yeah.
The temperature of the 77.3, how come we're putting into Kelvin? Should be canceling out 3 Celsius?
Oh, okay, fair enough. Good question. I don't know if you guys caught the question. This is in Celsius, right? So a change in Kelvin and a change in Celsius are the same thing. So I know that I've actually put Kelvin here and Kelvin here, but it's actually a change. So would you feel better if I put Celsius there? And I can convert this into Celsius and this into Celsius and do the same math and come up with the same number. So it will be okay if I don't, because I don't want to convert it. But I guess I converted this to Kelvin, so I could have just as easily converted that to Celsius. Okay. So it doesn't matter. And it's good to see that the change in Kelvin and the change in Celsius is the same. Okay. But I did really want you to see how I used conservation of energy, how I used the positive and negative of the Q, as well as realizing this is boiling, and it's hard to imagine something this cold boiling, but it is, because it's nitrogen and it's boiling away. Okay? And so there's our whole idea of liquid nitrogen. I'll tell you what, you guys remind me. I'll get some liquid nitrogen when I'm at UCSB sometime. So maybe over spring break, remind me. By that time we'll be in optics, but it'll still be worth seeing here. And maybe we'll cool a bunch of things down. Like racquetballs are great to cool down, because the flexible rubber is no longer flexible. The rose is no longer flexible, and so just some weird temperature things there. Yeah. So I'll try to remember to get some. Yeah.
I was just going to ask, between conduction, convection, and radiation, there's only 2 equations, right?
Oh yes. And
in the reading, I only saw it.
Yeah. Did you might have noticed? I'm glad you pointed out. There was no equation given for convections.
Yeah.
Convection is the flow of fluids.
Okay.
And we really need a whole class on fluid dynamics to understand that. Okay. And we just haven't got there yet in your education. Yeah, good point. So we only explained how it works, not really gave you the equation for the rate at which it works. Yeah, keep that in mind. Because again, many of you will, when you transfer from here, that'll be one of the first classes you take at UCSB or Poly or wherever you transfer. It will be fluid dynamics and how things flow based on their temperatures. I know some of you are even working with the more differential equation. This is a one-dimensional differential equation, but I think in Math 220, don't you do the 2-dimensional heat equation? Maybe it's even 3-dimensional heat equation. Yeah, so this is kind of a one-dimensional heat equation. Because again, we don't go past Math 160, but some of you are learning that math now so that next year you can get hit with the harder stuff and you can do math. So just like in 102, we didn't do anything with calculus. In this class, we don't really do anything with multivariable calculus. That's the next level up.
And then for the radiation part, do we do any calculus with that equation?
Not till the end of the semester. That equation, Stefan's equation, we're going to derive it with some calculus. Yeah. But we need to understand a little bit more about quantum mechanics and Planck before we can. So that's why we haven't done anything. Yes, the last unit is quantum mechanics. Yeah, so it's an introduction to quantum mechanics. Again, getting you ready for the next level. So, and really good stuff. I think you will find it exciting. And that's about the point where we hit in this class the differentiation between engineering and science. And that's why it's at the end of the sequence, and you know, some of you will need quantum mechanics, many of you will not. But everybody should be exposed to the general ideas. That's why we spend 3-4 weeks on quantum mechanics, and that's all we have. Yeah. All right, well, better try another one here, number 25, so I can really get to kind of 25 and 26. I'm going to probably cut short on 26, but I'll do that on Thursday. But I really wanted you to see these two. 25's got this little picture. 22. 26. I might have misspoke. Maybe it's 26 I want. Hang on. Yes, it is. Oh, no, it is not. Okay. I want to do 25 first, then 26. There's no picture for 25. So I'll start with 25 and then I'll get to that picture. But let's look at number 25. 25 doesn't give a picture, so I'll draw it here. But it says this. 1 mole of an ideal gas is warmed slowly, so that the gas goes from the PV state of initial pressure and initial volume to 3 times the initial pressure and 3 times the initial volume. Let me pause right there. This is what I want to draw for you. If I draw a PV diagram, and the point of picking this one is, just like the free body diagrams were very important in mechanics to help our thought process, the PV diagrams are very powerful here in our thermodynamics to explain what's going on here. And so what they are saying here is there is some gas that has an initial pressure and an initial volume. On a PV diagram, it would be right there. Now, keeping in mind the ideal gas law, the initial pressure, initial volume would also dictate an initial temperature, right? So I know that's not one of the grids or one of the axes on my grid, but this is a state function, if you will, PV equals nRT. If you know 2 of them, in this case pressure and volume, don't you also have a temperature? So there is some temperature. So there's initial pressure, initial temperature, and initial volume. Then, here's what it says. The gas is increased to a volume of 3 times. At the same time, the pressure is increased by 3-fold. So not only do we increase the volume, but we also increase the pressure. Now that seems kind of weird. How in the world could you possibly increase the volume and increase the pressure? You've got to be warming it up here, right? Because without warming it up, you would think expanding the volume means you have a lower concentration and the pressure should go down. And it would if you didn't change the temperature, exactly. So this is a case where we are obviously warming it in the process. And so it has said that you get to 3 times the pressure and 3 times the volume. So that means its final temperature is way up compared to the initial. How much is what the question's going to ask here. But it obviously has to be warmed by quite a bit. Yeah.
So on the PV diagram, there's pretty gradient field for temperature. As you get further from the origin, the temperatures are going to increase.
Okay. If you also throw in there, let's say the number of molecules don't change. But yes, for a given number of molecules. Yes. Right. Right. All right. So, as we continue to read the problem here, it says 1 mole of an ideal gas is warmed from an initial state of pressure and volume to a final state where the pressure is 3 times as much and the volume is 3 times as much. And it is done in such a way that it is directly proportional, that is, pressure and volume are directly proportional to each other. Now, why is that thrown in there? Doesn't the amount of heat and work depend on how you get from state 1 to state 2? Wasn't that my long discussion last week? last Thursday, I went on and on about saying be careful how you calculate something. It depends on how it gets there. And we talked about a bunch of processes like adiabatic was one of them, isothermic was another one, isovolumetric was another one, isobaric was another one. This is none of those. It doesn't even have a name, but it is saying it's proportional. So that much I know. What does proportional mean?
1-to-1.
Straight line, 1-to-1, right? You put it on a graph, you got a nice straight line. So this is not one of those fancy 4 that we talked about last time, but this is a process, and they tell us the path that it takes. And I needed to see that. Because here's the question. A, how much work is done on the gas in this process? B, how is the temperature related to the volume in this process? Well, why don't I start with the work? What did we learn in this chapter about the work? Minus the integral of PdV, right? That was our general idea, and it was the area under the curve. And last lecture we looked at 4 special cases: adiabatic, isobaric, isovolumetric, isothermic. Which one I missed? Oh yeah, isothermic, right? This one, like I said, is neither, but it would be the area under this curve. So what I can do is think of this as a triangle and a rectangle. Or I could think of it as a trapezoid, if you remember the area of a trapezoid. But I would just say, let's figure out this area under the curve. So here, the rectangle would have a height of T1 and a length of 2V1. Fair enough? Then the triangle itself is 1/2 the base, which is 2V1, and then the height, which is, oops, sorry about that. Can't even read my own graph. This was the temperature, not the height here. This is the temperature at this point. The height is the initial pressure. So the height is here, the area or the length of the rectangle is here. This is 1/2 base times height, and the height is 2p initial. So minus, looks like those cancel off. So I have a 2 there and a 2 there. So that's 4pi vi. And so that's kind of what they're after. How much work is done on this gas here? And so what they don't give me any numbers to work with, so I kind of leave it in symbols. It's initial pressure and it's initial volume. And it's 4 times that. Why is negative though?
No, work is leaving the system.
Yeah, what does the negative mean?
Work is leaving the gas.
Leaving the system, right. Leaving the gas. Now does that make sense? Is work leaving the gas? Because it expands, exactly, right? Work is done by the expansion. So as the gas expands, it's pushing the atmosphere back. That's what it's doing work on. It's got to push all the molecules in the atmosphere back. Or if there's a piston, it's got to lift the weight of that piston up, as you saw me do on a number of experiments here. That's where the work is going. So yes, it is negative here. Of course, we're also at the same time probably putting a very large flame underneath it. There is probably a lot of heat energy going into it to make the pressure go up and the volume go up at the same time. So yes, I'm putting a lot of heat into it, and I'm losing some of that energy because it's doing work on the environment. So this is half of the problem in terms of the thermal dynamics. This is how much work is being done. I'm also doing a Q. The other part of the question says, well, what's the final temperature? Yeah. And so when I answer A, and go over here to B, I can say, all right, what is that final temperature? Well, here's what I do know. I know that initial pressure times initial volume is equal to nR times initial temperature. And again, why I picked this one was helping you see part B. Remember this. I mentioned it last time, and I haven't got a chance to show you too much. I'm going to run out of time, but I'm going to show you more on Thursday. If you like puzzles, you're going to love this stuff. If you hate puzzles, you're going to hate this stuff. How do you go from one to another? How do I connect from here back to here? Here's a very useful connection. PV equals nRT. Okay? That is always true wherever you are on this PV diagram. So watch this. This is what I know for certain. I also know for certain that final pressure and final volume equals to nR times final temperature. So as I put these two together, knowing that the final pressure is 3 times the initial, and the final volume is 3 times the initial, nRT. Also noting that the 3 and the 3 make a 9, and the initial pressure and initial volume is nR times the initial temperature, matching nR final temperature, canceling an N and an R. I can answer this question, that what is the final temperature? The final temperature is 9 times the initial. And that's why I asked earlier, how in the world are you going to get this gas to not only get bigger but also have more pressure? And the only way is heat it up. You've got to have the temperature. And notice it goes up by a factor of 9. Why 9? Because we need 3 times the temperature if the pressure was just going to stay constant as we got 3 times the volume. But now we are not only having 3 times the volume, but we are having 3 times the pressure. So there's 2 factors of 3 of why the temperature needs to go up. One factor is more volume. Other factor is more pressure. Both of those went up by a factor of 3, so this temperature's got to go up by a factor of 3. So for this to work, whatever experiment this person is doing here, they are warming the gas in such a way that they are ending up putting 9 times the temperature. They're going to put a lot of heat in this. Factor of 3 again. All right, well, maybe we have time to just hit one more example. And won't really get to the big one. I'll wait for that on Thursday, and then we'll be done and go to the next chapter here. But 26 is the one I got started with here. 26, they put the diagram on the board there, and they say this. They say this one, a gas is taken through a whole cycle. That is, in this PV diagram, we start here at A and we go to B. Well, that's kind of like the problem we just did, a nice linear relationship on a PV diagram. But then we lower the pressure, keeping the volume the same, so this part is isovolumetric. That gets us to point C. Then we return to point A by changing the volume without changing the pressure. So that's isobaric. And so here's the question. A gas is taken through the cycle described in figure 26. A, find the net energy transferred to the system by heat during this complete cycle. B, what if this cycle is reversed? Well, we'll go to B in a second, or maybe we won't here, but I'm going to start here with A. And in this PV diagram, we start here at point A, going to point B. From B, we go to C, and C, we go back to A. And what I wanted you to see in this problem and the next one is kind of a nice setup that I think will help you as you start doing the problems. Not only have a PV diagram, but make yourself a little chart. And ask yourself, what is the pressure, the volume, and the temperature at A, at B, at C? Now, you may not have to fill in the whole chart. And for this problem, I don't think we need the whole chart. In fact, we really don't need the whole chart till the next problem, which we're going to run out of time, so I'll show you on Thursday. But this is a nice way of thinking about things. Also, you could calculate the process of this. How much work is done? How much heat is done? What is the change in internal energy when you go from A to B? When you go from B to C? and when you go from C back to A. In this problem, and again, too bad we're going to run out of time here, because this problem doesn't show the whole justification of why I would want two charts and every point on the chart. The next example will here. So we don't have enough information to answer everything about this in this whole chart. But keep this in mind. This will help you with the puzzles for those of you who are struggling. What we know is PV equals nRT over here, don't we? And so the key here is if you know any two, can't you find the third? And then what do we also know about this? Heat and work add up to change in energy. So again, knowing any two, we should be able to find the third. Okay? Now, this problem is a little bit easier than a whole chart, as I said, because this asks for the net transfer of energy through the whole thing. And the author should have used a better word there, because I think what he's saying here is not this from A to B, not this from A to B, not this from A to B, but what are they total? What about the whole cycle? And here's the key to this puzzle, and many puzzles, not all puzzles, but some puzzles. If you go through a whole cycle, if you go from A to B to C, there would be a change in internal energy from A to B, another one from B to C, another one from C to A. If you add those three up, what are you going to get? 0. Why? Okay, no change in energy, back at the same point. So why? There's a certain temperature at A, right? There is a unique temperature at A. It can be calculated if you know P or V. It doesn't matter how you left A, but when you get back to A, you know, since the pressure and volume are the same, what do you know about temperature? The temperature is the same. And what did we say was really useful about this number here? It's a state function. It only depends upon the pressure and the volume, right? It only depends on the temperature. And so what we are saying here is this gas that was first warmed to here, cooled to here, and cooled again. But once it got back where it started, the total change in energy would be 0. And so this problem might have looked a little bit hard at the beginning, but it asks for the total energies here, here, and here. Wasn't that easy? You just start at A, you end at A, you know it's 0. But does that mean these are zeros? No. But since they add to 0, don't they have to be equal and opposite? And that's the key to this puzzle, because if there is an easy way to get one of them, and there is this one, then don't I also know that one? So in this one, I would not ever try to calculate the Q. This would be very difficult calculating Q directly. What I could do, though, is calculate the W and the delta E and get the Q from that. That's the puzzle, the first law of thermodynamics. If the question said, find the total Q, don't solve it straight on, get the W and get the delta E. The delta E is easy. And I even think the W is easy. What's the W? The area under the curve. So if you go this way, you have the whole area under the curve. When you go back, you subtract off this area under the curve. So the total work must be the area under the triangle. I'll say it again. This way would be the whole area, including down here. But when you go backwards, then you would be doing a negative area. This would go away. And so we just need to know the area of that triangle. And that's pretty easy. Getting the area of the triangle is 1/2 Oh, we're out of time. What's the base? The base is 4 cubic meters. What's the height? Okay. 6, can I put 1,000 pascals? Because that's a 2, and a 2 times a 6 is a 12,000. Newtons times a meter is a joule. So this is 12,000 joules. Now I better be careful about the sign, right? Isn't the work minus PV, so this is really a negative, which means this Q is a positive. So I put in, according to this problem, I put in 12,000 joules of heat, and the gas expanded and did 12,000 joules of work. Hopefully I burnt the gasoline and the car is now moving. That's the key here. I burnt 12,000 joules of gasoline and I now have a kinetic energy of 12,000 joules.